Alright, now let's look at 1.3 modeling with linear equations. So we're going to learn how to write and use mathematical models, simple models right now. We're going to solve some extra problems. These are actually huge, so these are pretty big. And we're going to use some common formulas. So what is mathematical modeling? Well, the best way I think to put it is it's a formula that describes a set of data. Okay, and the idea is it's basically the mathematical expressions and such that go along with it. So, you know, there's a mathematical model for determining femur length, for example. Okay, but we'll get to that. So all it is something that describes, a mathematical statement that describes a situation. Okay, so the general concept, just keep in mind that keywords are very important, and just read the problem carefully. Now, I'm not going to go through each and every one of these. However, I will slow the video down just a little bit so you can take a look at each and every one of these specialized keywords. Keywords, you know, for equality, addition, subtraction, multiplication, and division. So these are all the keywords that we're going to see within our problems. All right, so let's get to it. So here are some more useful formulas. Now, what I'm trying to do here is just give you all the information up front before we actually begin. So we're just here to show you some useful formulas. Just areas and perimeters mainly for the basic shapes and volumes. I'm not giving surface areas for the cube or the rectangular solid or the sphere that you'll see in a second. But where is the sphere? There it is, in the cylinder. But we will use these eventually in each one of our processes. So these are just basic formulas that we can use. And you can pause the video and look at each one or return to this section when need be. Okay. So the last ones for the specialized formulas are the temperature. And I've given you just the Fahrenheit model here. And I'm asking you, how do we solve for C? Well, you know, this is just a reminder, but it says that we multiply by 9/5, then add 32. So the opposite would be subtract 32, then multiply by what? 5/9, right? The reciprocal, because that's what we'd be dividing by 9/5. But dividing by 9/5 is really multiplying by 5/9. So if you can see this, this is just going to be f minus 32 times 5/9. So that's just a little reminder on how to solve equations pretty quickly and go back and forth. Okay, so all of this, the first temperature model does is just do a conversion and looking at Fahrenheit or degree or Celsius scale. Simple interest is just that the interest is equal to the principal, and the principal is the original amount. Okay, R is the rate, and T is time, and that's in years. Compound interest is given by the formula here, in which case the balance equals the principal times 1 plus the compounding rate, so that's an R. I know it looks like an N, but I'm going to make sure it looks like an R, and that's an N. So what is N? N is the number of compoundings, or the rate of compounds, so number of compounds, we'll just say. And R is the rate, and then NT, the number of years. So it's, what we're looking at is really the whole plus the compounding rate. And it's exponentially driven. Okay, so once we actually start to identify the problem and read it, we really have to look for those keywords, and they will really help us obtain the mathematical operations or statements that we'll need. So the idea here is to read carefully, looking for those keywords. You want to describe the variables. Now that'll be something like, let X be number of cars, or something like that. Something that defines what the variable is. You might want to produce a table in order to help you find the mathematical model. If you don't need that, you can find the mathematical model, the expression, or the equation directly if the problem presents itself, and then you can solve. So let's look at our first example here. A rectangular room is 3 times as long as it is wide, and the perimeter is 100 feet. Find the dimensions of the room. Alright, so now let's look at our first example. And I've already taken the liberty of putting a few things down to help us get along with the first problem. So it says a rectangular room is 3 times as long as it is wide, and the perimeter is 100 feet. Find the dimensions of the room. So what I did was I started to highlight and utilize the key words. So the rectangular room is going to tell us something about the formula for perimeter, and we now know that we're going to be using that. So we should put that down in a second. The other thing that we know is that one of the distances is 3 times bigger than the other. So it's 3 times as long as it is wide. So what I did then was I went down here and I defined the variables. So I said let W be width of the room and let L be length of the room. Which means that by the reflexive property that W is W, or the width is the width, and the length, because of this statement right here, tells us that the length is equal to 3W, because the length is 3 times the length of the width. So we can now put this number here as 3W. Now all we have to do is calculate the perimeter, right, for the dimensions. So, well, how do we do that? Well, there's only one dimension that we have to care about, really, because everything is with respect to W. So if we do this now, then we can say that the perimeter with respect to W is equal to 100 feet. So we know that. But we also know, so maybe I'll do it this way. We also know that the perimeter is equal to 2 length plus 2 width. So all we have to do is do a small substitution and work the process through. So let's work this out. We know that the perimeter is 100, and we know that we have to take 2 times the length plus 2 times the width. So let's use W pink. So if we put this in, it's just going to be W, but if we put the other one in purple, it'll be 3w. So we just did a substitution. Now notice what we have. We have an equation in one variable. So that allows us to solve. So let's do that. And this will be what? 100 is equal to 6w plus 2w, which tells us that this is 100 is equal to 8w, which means that 100/8 is equal to w. And if we reduce this, well, if you don't see it right off the bat, well, we can divide both by 4, right? For sure. So that'd be 25 halves. So we now know that the width is 25 halves. Okay, so that's great. Well, we can do the division and find out this 12.5, but let's calculate the length. So if this is the width, what is the length? Well, the length is equal to 3w. So let's do it this way. So I'll just replace the w now. We'll use orange, and that would be 25 halves. And now what we can see is that the length is actually equal to 75 halves. And let's just put the units in as well at this point, so we don't lose them. All right, let's move on to example 2. And what we have here is the sum of two consecutive numbers is 525. Find the numbers. So what are we looking for? Well, sum, that tells us that we're going to be adding two things. So we're going to have two consecutive numbers. Well, what are consecutive numbers? Well, 1, 2, 3, 4, 5. They all follow a suit. So consecutive be something like 1, 2, 3, 4, 5, all the way up to whatever. And now we know that there is some kind of value that it does reach, so the sum of these two things is 525. So how can we set this up? Well, we first have to maybe come up with some variables. And let's think about this for a second. If we pay attention to the idea of what consecutive numbers are, and let's just say we let a number n, let's just say n is a number. So if n is a number, and I'm starting at 1, what would be the expression for the next number in the sequence? Well, that would be, I start at n, and then how many places am I moving? 1. So when we look at this all together, and we start to think about the consecutive numbers, and I'm going to write it this way. So the number n plus, well, how do I get to the next step? N plus 1, right? Because it's one more step bigger than n, and that must be equal to 525. So what we're saying here is that this is the first number, and that this right here is the second number in the sequence. So now all we have to do is combine, and this looks like it's going to be easy. It's 2n plus 1 is equal to 525, which means that 2n is equal to 524, which means that N is equal to 2, 6, 2, looks like. So if N is 262, then the next number is N plus 1. So N plus 1 would be equal to 263. And if you do add these two numbers up, you should end up with the 525. All right, now let's finally tackle a mixture problem, okay? And here's one of the most basic ones that you can do in any chemistry class, and it's just a nice way to save you money in the long run. Labs do this all the time, pharmacists do this all the time. So what we need to do, so let's go through the problem first. You need a 15% acid solution for a certain test, but the supplier only ships a 10% and a 30% solution. Rather than pay a surcharge to have the supplier make the solution, you decide to mix some of the 10 and the 30% solutions to acquire the 15% solution that is needed. If you need to make 10 liters of a 15% solution, then how many liters of 10 and 30% should you use? So, if we tackle all of this, one of the big things is obviously a keyword mix for mixture. The other thing that's really important here is actually the very last sentence. It really, or the last question here, it really does put together everything that we're going to need. So if you see this, we're going to need to make 10 liters of a 15% solution. So we're going to need that. And what are we going to need to make it? Well, some amount of these two solutions combined. So that tells us what we can do, and we can define our variables. Now, when defining variables, it's up to each and every individual. As long as you make the definition known in the very beginning, the problem should have no issues with trying to see where you're going with it. In other words, you can define your own variables. You don't have to use the ones that I'm using. So I'm going to say, let L be the 15, no, not the 15, it was 10%, that's right. Be the number of liters of the 10% solution of acid, and I'm going to let H be the number of liters of the 30% solution of acid. Now I'm doing this only because I'm thinking in this that this is the low concentration and this is the high concentration. But you can call it anything you want, X or Y or whatever. But now that we have defined the variables, we can now work with them. Now, whenever you're confronted with a mixture problem, my first advice is to make a table. So, in the table, what we want to do is label some of the aspects that we need. Well, we need to know how much of a 10% solution we're going to use. We're going to need to know something about the 30% solution that we're going to use. And we're going to need something about the mixture, which is the 15% solution. So I'm just going to write mixture underneath that. Okay. So these are going to be all the amounts of things that we're going to need, right? So what are the other aspects that we know or could find out relatively quickly within this problem? So, well, what do we know? Well, we know that we have those three things to work with. We also know that we're going to need the number of liters. Well, the number of liters are going to directly change the concentration. That's what we're trying to do, is get to 15%. So we're going to need to know the percentage of that solution, or the percent, acid or solution. And then finally, we're going to need to know the total of which we're going to use at each percentage rate. So that looks like what we'd have is the total amount that we're going to be using. Maybe I can simplify this a little bit more. Yeah, maybe what we'll do is we'll just say total liters of acid, or the solution. That would be on the So, well, let's play around for a second, and let's say that we're definitely going to need to know the number of liters for the 30, the 10, and the 15%. So, what I'm going to do is I'm just going to finish off the table and just try to clean it up and make it look a little bit nicer before putting all of the information in. Just keep in mind that what we're trying to accomplish is to find some mathematical model, M, that I'm going to call here for mixture, in relation to one of the variables. In this case, I'll say H. Why not? So if we can get one function in one variable, this becomes easy to solve. So based upon all of this information, I'm going to let the 30% amount be H. Well, if that's the case, and we had how many, what was the amount that we needed? So the amount of solution needed, that was 10 liters, right? So if we know that we're going to make 10 liters and so many of those liters are H, then it stands to reason that 10 minus H is actually the number of liters of the 10% that we have left over. So let me say that again a little differently. Because we are making a total volume of 10 liters, then we're going to fill some of this up with the higher concentration of stuff, which means that to get to the 10 liters, we're going to have to be at 10 minus whatever we took away, or already placed within our volume that we're calculating. So this is a nice way to start to generate one equation in one variable. So now the mixture, if I put this in, would be a combination of these beasties right here. But I think that's going to complicate the issue, so let's actually move on to the next thing, which is, well, what are these going to be able to, what are they as a percentage? Well, this is 30%, so what is 30%? Well, that's just 3/10, right? And what is the percentage for the 10%? Well, that's just 1/10. You could use the decimal equivalents and such, not so much, but it's just easier to use these in the end result. And what is the one that we want? Well, that's going to be 15 out of 100, right? Because that's 15%. And then we could just reduce this down to 3/20ths, okay? Because each 15 and 100 both have a factor of 5 in it. So this does help, and you know what? We could leave this, but pretty much going to use this one right here. You'll see why. Okay. So then what is the total remaining items left over? Well, the total liters of acid that we can use for the 30% is just going to be 3/10 H, right? 3% of the higher concentration. And that means that what we'll have left over is 1/10 or 10% of the leftover, which is 10 liters minus the number of liters at the high concentration. So the only thing we need to know now is what is this beast right here? Well, if we remember and we go back up to the original equation, the original problem, we want a 10 liter of a 15% solution. So that just means that we have 15% of a 10 liter solution. Well, that just means that we're going to have what? Well, that looks like we're going to have, well, that cancels out with that, which means that this looks like 1.5 liters in total is what we're going to be looking for here to create this mixture. So if we take the total of the two different concentrations and put them together, we should acquire, in addition to a 1.5 liters for a total solution. So because we now know how much of a total amount of the mixture we're going to need of the 30 and the 10 at the 15% level, we can now express the model using the very last column. So, well, what is the mathematical model? Well, the mathematical model in this case is 1/10 the quantity 10 minus H, then plus 3/10 H is equal to 1.5. So we have an equation, one unknown. Okay, so that means we can solve for H. Now, I'm mixing decimals and fractions all over the place here, and there's a reason for it. But if I go back now and just remember what I told you earlier, that I'll be using the 1500ths instead of this. So I'm just going to rewrite the problem. Making sure to realize that how many tenths is this? So what I mean, how many tenths? Well, that's 5/10, right? So it's 1 5/10. So that would be, oh, that's really easy. That's just 15 divided by what? 10. Oh, that's nice. That's nice. Why is that nice? Because we're only dividing by what? 10. So if we wanted to clear denominators, what would we have to multiply everything here by? You got it. So if I multiply this by that, well, 10 divided by 10, right, is 1. So that just leaves 10 minus H. Then 10 divided by 10 is 1. So that just says plus 3H. And then the last one over here, green, is going to be, well, you're multiplying and dividing by 10, so that equals 15. So now all we have to do is combine like terms and solve, right? So if we put all this together now, this looks like it's generally going to be 10 plus 2h is equal to 15. Or what? H is equal to, let's see how good you are and see what we did here. And I'll say it's 5 halves, or 2.5 liters of the higher concentration. Okay? So how did I do that? Well, I just subtracted 10 from both sides, and then I divided by 2. So, if we need 2.5 liters of the higher concentration, then all we have to do is ask ourselves, well, how much do we need of the lower concentration? Well, that's easy, because remember that L, well, I think I used a capital L here. So capital L was equal to 10 minus H. But now we know that H is 2.5, or 5 halves, liters. So if, that's too many L's, liters, then that means that L needs to have 7.5 liters. So the solution to the solution problem is going to be what? 2.5 liter, comma, oh, no, not comma, let's do it this way. You know what? Let's not label it like this at all just yet. But let's write it down. So we need 7.5 liters of the 10% solution combined with 2.5 liters of the high concentration, which was 30%, to make 10 liters of a 15% solution. Let's move on to example 3. You have $30,000 to invest and would like to invest some amount of money into 2 different stocks. One stock yields 22% return. Holy moly, that's amazing. And the other yields 40% return. Yeah, you just hit jackpot. You can basically find any place to work and retire. So if you are to make a 35% profit given both stocks, then how much should you invest in each type? Now, again, this might not look like it, but it is, again, another type of mixture problem. Okay? So we're going to have to do some definitions, right? So we're going to have to define some variables, and then we might have to make a table and work the process through. So how about we just do A and B? So let's define A as amount to invest in stock 1. And let's let B as the amount to invest in stock 2. Then, and we also know a few other things, that we have a total, so I'll just write that down, a total amount of 30,000 to invest. Okay. So this lays out all of the problems, and you can start to see where this does become a mixture problem again, because one stock is going to yield 22%, another is going to yield 40%, and they're going to combine to make a 35% profit is what you're hoping. So now that we have defined the variables, well, we should probably set up a table to help us with these, right? And we can really define one of these stocks in the other. So what do we mean by that? We're going to try to define either A as B or B as A. So just like in the last example, we related two different aspects of the solutions, right? Two different solutions, but we related it down to one. So if we look at this and we decide to say that, well, we'll do the same thing that we did last time. We'll say that we want the 35% through a 40 and 22% mixture. So if we let A as the amount to invest in stock 1, then B alternatively becomes 30,000 minus A. So do you see what we did there? What I'm trying to get at when I say express A as B or B as A. So now we can generate an equation in one variable. So all I did was set up the table here, and I set it up so that we have the two different components that we're going to mix, the mixture environment, the amount to invest, the desired profit, and the total that we're going to invest entirely at the desired profits. So all we have to do is now label where or place in the table where our value should go, or our variables. So in this case, we said A is basically A. And we said the amount to invest in B is 30,000 minus A. And the desired profit at A was 22%. So that's 22 out of 100. And for B, it looked like it is 40%. So that would be 40 over 100. And then I'm not going to do any of the reductions here right this minute or anything like that. Although we should, but there's a partial reason why I'm not going to do it. So, well, what is the total to invest at A? Well, that's going to be 22% of A. Well, what would be the total that we're going to invest in B? Well, that would be 40% of what's left over from the 30,000 after investing in A. And then if we look at what we desire to get a 35% return on the 30,000. So that would be 35 hundredths of 30,000. And the reason I'm writing it this way is because we can see that we're dividing by 100. We're also multiplying by that 100. So this really crunches down to 35 times 300. And then all we have to do is multiply the 3 times 35, which is going to give you 90 and 15, so 105 with 2 zeros. So it looks like we're hoping to gain about $10,500, okay, at the end of everything, if all the rates and the desired profits stay true. So all we have to do now is take the last column and solve. So if I rewrite this down, I'll keep it all in blue. So that's 22/100ths A plus 40/100ths of what's remaining must be equal to 10,500. Now, again, there's a lot of ways that you could look at it, but don't think of it as this is the only way. I mean, I could have rewritten it and just put this whole piece in this area here as well. I didn't choose to do that because I didn't want to. I wanted to make sure that it wasn't overly complicated. Okay. So now the only thing that we have to do is solve for how much are we going to invest in A. So we could multiply this whole beast by 100 because we're dividing everything by 100, which then tells us that 22A plus 40 of this beast must be equal to this beast. Now what am I going to do? Well, it's 10,500, but it's times this 100, so I just have to tack on 2 zeros. Alright, so now we're just going to do the basic distribution, boom, boom, and I'll rewrite it as 22A plus, well, I'm just going to write this as 40 times this value right now for a second, minus 40A is equal to this value there. And the reason I'm just separating this out for a second is just to make sure and that you can see the multiplication without too much of a problem here. But if we do the multiplication, then this is just going to be 12 with 4 zeros, except we need that last one, the 10, right? So if we multiply those, we should end up with that. Okay, now do we have more negative A's or positive A's? Well, it looks like we have more negative A's here, which is kind of interesting. So, well, let's put this together here. Okay. So, where was I? Oh yeah, we were combining these. So that's going to be what, 18? So negative 18A looks like. Because 18 and 22 make 40. Okay. And that's going to equal this beastie. So then all we have to do is solve. So let's do that. We'll take negative 18A. I'll do it the classic way here, right? This is positive, so over here will become what? Negative, so that's negative this one. So that looks like it's about negative 150,000. And then if we just divide that by the negative 18, we get an approximate answer, actually, of 8333.3. And I'll just leave it at that moment right there. So this would be the amount to invest in stock 1. Okay. So it's easy to calculate the remaining amount now. Because all we have to do is do that subtraction, right? Because we know that B is equal to 30,000 minus the A, which in this case is 8333.3, roughly. And this is an approximation. And that would equal 21666.6 repeating or so. Okay, but that's, again, an approximation. Okay. So, well, what does that mean? That means that we need to invest approximately $8,333.30. 33 cents. Approximately this in stock 1 and 21,666 and like 60 cents or so approximately in stock 2 to obtain 35% profit. All right. So why don't you try this one on your own, and we will discuss it in class.